The last talk for this session will be given by Bharathan, a research scientist in Amazon working on sustainability. He's interested in developing methods and systems that help make the world a better place by reducing waste through education and with automation. So with that, the floor is yours.
Thank you, Abel, and thank you for inviting me to this workshop, Norman. It's really great to see this workshop and all the great speakers. I've already learned a lot from the talks before. A lot of the work I'm going to talk about today is work I've done outside of Amazon, primarily at UC San Diego, where I did my PhD. Actually, Professor Kleisel, who gave a talk in the previous session, was in my dissertation committee. So you would see some of the overlap here. So climate change is something that this group knows a lot about. So I won't go on much about that, except adding that a lot of corporations are also signing up to become carbon neutral. Climate pledge is something that Amazon started, and over 200 companies at this point have signed up to be carbon neutral by 2040. And in this talk, I'm going to focus on buildings, which constitute about 36% of energy, 40%, 39% of the carbon emissions if we include both construction and everyday electricity and gas use. And it gets roughly divided between commercial and residential buildings. My talk is going to focus on the office buildings kind of environments, but residential communities obviously represent a big part of this pie as well. And if we want to get to carbon neutral buildings, we kind of need to reduce the energy that they use. If we simply rely on renewable energy, wind energy, solar energy, even when they are growing so fast, the demand growth is even higher, and it will not be able to meet all of the demand with just the renewable energy. And energy efficiencies is a key part of the solution. International Energy Agency estimates that we need to make buildings about 30% more efficient to meet the goal of carbon neutrality in the building sector. So I'm going to propose this framework of sense, act, and scale. Sense is understanding what's in the building, acting on that information, and then scaling our solutions to thousands and millions of buildings. And a lot of the work that I'm going to talk about is research done on the computer science building in UC San Diego, and just want to acknowledge that for all the research that I'm going to talk about. So I start with sense, which is a key data point to understand what is happening in a building. Fortunately, there are many, many sensors already installed in modern buildings. And in a typical building, it's easy to find hundreds, if not thousands of sensors. However, these sensors are designed at time of construction. So they're kind of fixed as part of the building infrastructure, and buildings have a lifetime of 50 years or more. And as time evolves, sensor technology has evolved very quickly, but adoption of these sensor technologies in buildings is quite slow because replacing these wired sensors is really expensive. So the obvious jump is to go to wireless sensors. But even if wireless sensors have been around for more than 20 years now, we don't see much of an adoption in buildings. And the major reason is that the building infrastructure industry does not think wireless sensors are reliable enough. And they can be inexpensive. We can install them anywhere. The wiring part of it goes away, both power and the power part still might be a question that we need to look at, but the network part, the wiring is not required anymore. So we, about 10 years ago, started installing these wireless sensors to see how well they work. This is an occupancy sensor we developed, and this is the sensor was powered through batteries. And we found that the power consumption can be a major bottleneck in deploying these sensors at scale, because when you have thousands of these sensors, at least a few batteries are running out every day. So someone has to go and manually replace these sensors. And this becomes a major bottleneck in terms of adopting these wireless sensors. So to attack this problem, we created energy harvesting sensors where the battery is replaced by a supercapacitor, and there is a small solar panel that captures energy through ambient light. And this was much better than the previous sensor with battery powered because we need not have to ever replace batteries. It just keeps working. And the lifetime was about 2 days if it is continuously sensing, let's say every 15 minutes, sending a packet of sensors. And in this case, we had a whole bunch of sensors like motion, temperature, pressure, humidity, typical ones that you would find in a building. So this is good, but lasting for 2 days is not sufficient for an actual solution in a building because you're going to have vacation times, you're going to have long weekends, and when that battery dies, it takes 7-8 hours to charge back up because of the cold start problem with these supercapacitor chargers. And that essentially means that this is not going to work at scale. So we have these 3 types of sensing solutions: wired, which are great, but inflexible, expensive to upgrade; wireless work in terms of communication, but the battery power could be a problem. If you can find wired power, that can be a source of adoption. And this wireless plus harvesting solution, energy harvesting solution, can provide the power that is required, but it doesn't provide us reliable data. So can we make critical applications work on top of that sensing technology? So we kind of zoomed in onto this unreliable part and kind of sought out if we can apply methods to improve that. And we applied reinforcement learning for that, which is a form of machine learning where an agent learns from trial and error to achieve an objective. So in the case of energy harvesting, we have an agent which decides when the sensor should be on or off. And it is acting based on the information like the light level in that area and the amount of energy it has in its supercapacitor, the time of day, day of week. And the agent is rewarded if it is able to detect the events in the environment. And if the node dies because it has wasted a lot of energy, then it gets a big negative penalty. Initially, it's going to start doing random on and off actions, but the reward function will tell it how it's capturing events or not. And then over time, it learns how to schedule these sensors so that it captures all the events. So we actually deployed this solution where the agent is trained in simulation and the sensors are deployed in the real world. And with over 50 sensors where we had an A to B testing or apples to apple testing where the battery powered sensor is plugged in right next to the energy harvesting solutions. And we find that the energy harvesting sensor captures 93% of the events. And this includes the motion, temperature, where temperature is kind of like a delta change in temperature is considered an event. And the energy harvesting sensor never died. We deployed this for at least 2 weeks in time with all these sensors, whereas all of the battery sensors died in a week. So that kind of gave us a proof of demonstration that this could be something that we could deploy. However, 93% is not necessarily the same as what you would want from a critical application requirement. The 7% lost could be someone who is uncomfortable in the office or has some other kinds of critical needs that needs to be satisfied. And we have to go back to these wired sensors or wireless sensing. So overall, the sensing technology that we provide has to kind of take the cost into account, but also the reliability of these wired, wireless, and harvesting solutions. And how we use the mix of these technologies really depends on what we want to do with it. And that brings me to acting on this data. So we have all of this data. What can we do with it? If we take a look at how buildings are typically made more energy efficient, they go through what is called as a building commissioning or building retrofitting. You hire a contractor, the contractor would go through all the different equipment, infrastructure, look at the data, calibrate the sensors, instrument add more sensors if needed. They'll observe that, identify faults, fix those faults, upgrade the equipment, upgrade the configuration settings. And then you finally have an optimized building where they will say, oh, you saved 20% energy after fixing all of these things. This is a very good method. It works and it is applied at scale today. However, there are things that we can do better. This requires an upfront investment from the building owner, and the return on investment can be as large as 10 years. And a lot of these systems have kind of remained standard because there is no flexibility of innovating on top of this infrastructure. A lot of that is kind of stifled because the infrastructure is vendor locked. One vendor kind of takes over the entire building, and then even a small software version upgrade can be a pretty challenging task from a building owner's point of view. And if we compare this with the IT industry, we have standardized hardware, we have common interfaces, there is a whole bunch of applications, and one application on any phone looks the same regardless of where you are and what phone you're using. How can we bring this to the building industry? So we created a web-based kind of an operating system on top of buildings. The technology itself is not like an improvement over the state of the art. It's pretty standard. It just requires will from the building industry to adopt these and expose the information to third-party applications. And I'm going to talk about different applications I built on top of that computer science building and how this can lead to innovative ways of saving energy. So there are 3 applications I'm going to go through, and it's going to focus on the HVAC system, which stands for heating, ventilation, and air conditioning, because they constitute about half the energy consumption of most buildings. So let's start with occupancy sensing. If we take a typical HVAC system in a building, they turn on at 6 a.m. or so, and then turn off at 10 p.m. The exact times might differ from building to building, but they remain on for us on a fixed schedule. And a typical office schedule does not look anything like that. People come in late, they have a lot of breaks, and they leave early. And this, we could save a lot of energy if we control the building based on the actual occupancy information. And this is something that this community has done a lot of research on. And one of the, apologies. I think I should. So HVAC systems is something with occupancy sensing of HVAC control, something that the e-energy and BuildSys community has done a lot of work on. And what's interesting about these HVAC system, the infrastructure, where it has been designed for since the 1990s, already accounts and takes into consideration occupancy of the individual parts of the building. If you only had the occupancy information, you could control it and save energy. But reliable occupancy information in a privacy, non-invasive manner is quite challenging. You can't just install cameras everywhere, and you can't just ask people where they are at any moment. So how do we sense occupancy in a scalable and non-invasive manner remains a challenge. So I created a simple solution that used the Wi-Fi infrastructure in the building, where the general assumption is that if you have a phone or a laptop, and that's connected to the Wi-Fi infrastructure in the building, then you are in your office. And with this simple assumption, we get a very good approximation of the occupancy of the building, and we can control the building based on this information. So looking at a study of over 100 participants, this is what a trend looks like for a week. And what's surprising here is that out of those 100 occupants, the peak occupancy of the building is only 40. And of course, it undulates over time, and Mondays most occupied, Fridays least occupied, and so on. We actually controlled the building based on this information and saved about 18% in electricity. And here also, you can see the occupancy patterns over the day, where over 100 people are being sensed by the Wi-Fi infrastructure, and the peak occupancy is still around 40. So the key part of making the solution work was not the algorithm, not the data, but just accessing all the different kinds of information and connecting them together. The next application I want to talk about is fault detection, which can be a major issue on buildings. In the UC San Diego building, more than 50 buildings were connected to a building management system, and faults were being monitored, but they would see more than 10,000 faults per day. It's just not feasible for a person to go through that and look at which faults are important. So they simply rely on calls from the occupants or high priority things that they notice from the sensor data, from the dashboards. And essentially all the fault detection algorithms just don't work. And a whole host of algorithms have been published in literature, but they're simply not adopted because the vendor system is locked and you cannot deploy any algorithm that you want on top of the building. So we created our own algorithm. The algorithm per se is not like the next best algorithm in fault detection. It is a fairly simple algorithm, but the access to the data and able to deploy that algorithm, it made all the difference. So in our case, the algorithm depends on comparing two different entities which look similar to each other. So we model based on the energy consumption of a thermal zone in the building, and we compare different thermal zones and see which of them stand out. And those are anomalies that we look into further for creating fault detection rules. And we found a host of different faults by this method. There was overcooling, the software configuration of the thermal zones were incorrect. There were rooms which were cooled when it was supposed to be off, and it was not cooled when it was supposed to be on. So all of these faults were surprising, even to the facilities management who have been managing this building for over 10 years. And we found 88 such faults after a building operator went through the entire system and fixed all the faults they could find. And that corresponds to about 400 megawatt hours per year of savings. Finally, I want to talk about human interaction. This is an application that Professor Kleisel also touched upon briefly. We interact with the HVAC system through a thermostat. And a thermostat is great from a design point of view. It actually has all kinds of information that you would want, like the temperature, the LED, which indicates that the HVAC system is on or off. There is a slider for you to change the temperature setting. There's a button. So if you come on nights and weekends, you press that button and the HVAC system will turn on for 2 hours. But in practice, that lid is actually closed. And many people don't even realize that there is a thermostat in their room. And they were uncomfortable. They didn't know what to do. They didn't know who to contact. And just because they were cold, they would come up with their own solutions, like taping a manila envelope onto the duct tape on the ductwork so that they don't feel cold anymore. And that actually exacerbates the problem because then other rooms get even colder and so on. And this is not something that is unique to the computer science building in UC San Diego. I've noticed that in many buildings. This is an example from of a thermostat in Carnegie Mellon University, where they had to label that this is the HVAC system. To solve these, I created a software version of a thermostat. It has all the same functionality, such as showing the temperature, letting you adjust the temperature, turning it on and off if you're coming on weekends, and an additional functionality which lets you give feedback, whether you're feeling comfortable or you are uncomfortable and want to complain about it. And we also included an energy usage meter whose color will change based on how your energy consumption compares to your other thermal zones in the building. And this energy estimation is done through some heat transfer equations that we do with the help of sensor data that is available from the HVAC system. So the result of this, the solution has been deployed in the building for 10 plus years now. And the occupants of the building were much happier with this system. As you can see, just from the survey and interviews, they were finding the software thermostat to be much a better experience than the previous version, the traditional version. One thing that the facilities management were worried about was that, oh, this is going to generate so many complaints and we don't have time to address the complaints that we already receive. How are we ever going to manage this system at scale. But we find that most people don't complain. Only 8% of the activity is about feedback. They are happy to manage their own comfort. And when they do complain, there are significant faults that we could not have identified through just sensor data. Like a fridge was blocking the thermostat and someone pointed that out, and then you move that fridge so that the entire HVAC system works much better. So overall, it was very well adopted and led to a much happier occupant experience. And just something that we did very recently, we used reinforcement learning to intelligently control the HVAC system, and that can lead to saving of energy. Here's about 70% of total energy. I will not go into the details of this for time reasons. So in summary, one, minimizing waste is really challenging, and we should exploit all the data, all the tools that we get. Accessing that data from the building, controlling the building in an automated manner, and opening up that infrastructure is really key to innovative applications on these buildings. And finally, tying it back to the sensor data that we have, whatever we are acting is based on that data. And maybe there is a return on investment pitch that we have to make every time we are designing on an application. What is the minimum amount of infrastructure that we need for that particular application? So the people who are adopting it see that they will get the gains of that application quickly. Finally, I'm going to talk about scale, if the time is okay. So the scale,
we can have like 3-4 minutes of talk and then wrap up by 12:45. Give like 15 minutes for lunch. So yeah, okay, that would.
Okay, yeah, I'll wrap this up soon. So these solutions that I talked about are one building solutions. They have to scale if you want to apply this to lots of buildings, and that is a critical bottleneck in terms of adoption of these solutions. So we actually tried to deploy that solution to lots of buildings and quickly hit a bottleneck, where we found that each of these buildings are very different from each other. Their infrastructure is different, their age is different, they have been changed over time, and a lot of this is not documented at all. So before you even start the software deployment solution, you need to go and spend a lot of time in the building, talk to the building operators, look at the building plans, and lay out the infrastructure in some format that a computer can understand, and then you can start deploying. So this is the scale for scaling, this becomes the bottleneck. So to overcome this challenge, we proposed the brick schema, which standardizes all the infrastructure in a building and exposes that as an API to third-party applications. Brick was developed in collaboration with about 7 institutions, and it's gaining adoption. Here is an example of a toy building where you have 2 rooms, a small HVAC system, and a lighting system, and they translate to become a graph that you can query, and you can figure out what sensors are there in the building, where they are located, and so on. The query is all machine programmable, and you can do data analytics on top of it. This is the 8 institutions that I was talking about, and you can go to brickschema.org to learn more about it. There is still the problem of mapping all of that building information to the brick schema, which is an additional challenge that can benefit from machine learning based solutions. I'll pause there and not talk more about this, and kind of conclude the scale part of the talk, where agreeing on a standard is a key part of making these data available and making the applications on buildings portable, and scaling these solutions. One of the aspects that is also lacking is data sets. There is very few data sets that are openly available in this space. And if we have data sets, then you can apply all of those machine learning techniques that we're talking about at the workshop. And that would also spur innovation in these deployment settings. And I hope that when we deploy all of these infrastructure parts, there's lots of applications that are waiting to be invented, and we can make buildings a lot more efficient. So with that, I conclude. We need sensors. We should exploit that sensor information and expose that information with standardized formats. And then we can develop a lot of different applications on top of that. And when we have all of that, you can control them with Alexa. And thank you. I'm happy to take questions.
Thank you, Bharathan. I think Vivek has one question. You are muted.
Yeah, is it audible?
Yeah, now.
Hi, Bharathan. Thanks for the great talk. I have a question regarding scalability. How a typical reinforcement learning solution, when it is being scaled for multiple users or the multiple buildings, how the scalability issue gets addressed when we want to train the agents. Typically, a solution has been trained over a particular building, a specific building. How do we scale it over a number of buildings wherein the learning has to be done again? So typically at a high level, how the scalability has been addressed in a reinforcement learning approach?
Yeah, that's a good question. There are multiple ways we can go about it. So in the energy harvesting solution, where we had a scalability problem, not just per building, but per location, because every location had different patterns of energy and events. And we needed to have policies that were specific to that location. And we actually developed a solution using meta reinforcement learning, which learned from these sensors in a collaborative way and without any historical data and without any ways of like just deploy these hundreds of sensors at a time. You can start optimizing the sensors concurrently, and that way it scales, and the more sensors you have, the faster it scales actually. So it's great from that point of view. So one word answer is meta reinforcement learning. Another solution, especially the one I talked about briefly, which is the building control, is offline reinforcement learning, where you're exploiting historical data. So if you have historical data, that's like a gold mine that you can dive into and come up with learned policies. And that historical data then can adopt in many of the machine learning solutions like domain adaptation, self-supervised learning, that reduces the reliance on a particular domain-specific data.
Right. Thank you. Thank you so much.
Thank you.